Now we understand the common source amplifier and also the limitations caused by the transistor's output conductance and so on. Now in this lesson we will look at some practical aspects of a common source amplifier and in general any amplifier. The point is that the parameters of a transistor or in general any active device, semiconductor device, vary quite a lot. Okay, that is, if you realize a lot of transistors and you nominally intend to have the same current factor and same threshold voltage and so on, in reality they will come out to be different from each other and also different from one manufacturing batch to another. Okay, and also like many semiconductor characteristics, these things are strong functions of temperature. Okay, now these will have some effect on the amplifier performance. We will first see what that is and try to come up with techniques that fix these things to the extent possible. Okay. So let's say the transistor is operating at some operating point. It has some VGS, some VDS and a certain ID. Okay. Now the small signal parameter of this GM, we know it is mu n Cox W by L VGS minus VT. Okay. Again I am ignoring the 1 plus lambda VDS term. And also the output conductance GDS is lambda times ID. Okay. So these are the parameters of the small signal equivalent circuit. In the small signal circuit, we will have GM VGS, where this is the incremental VGS, and we have the conductance GDS. Okay. Now, how did we set up the operating point in our common source amplifier? Basically, we wanted a certain GM, and from that we found the VGS. And the way we fixed the operating point was to fix VGS to the desired value. Okay. So if you recall, our circuit looked like this. I am not drawing the complete circuit, but only the part that fixes VGS. And in our particular example, we had a 23 volt supply and an appropriate ratio of resistors such that the operating point VGS was equal to 3 volts. We fixed VGS to 3 volts. Okay. So now let's see what happens with this type of setting up of the operating point. So GM is mu n Cox W by L VGS minus VT. And as usual, I will consider the threshold voltage to be 1 volt and mu n Cox W by L to be 100 microampere per volt square. Okay. Now, in our circuit, this is fixed at 3 volts. So clearly, if you calculate this, this will come out to be 200 micro Siemens, which is what we wanted. Okay. Now it turns out the threshold voltage of a transistor can vary considerably. Okay. So let's say it varies from 0.8 volts to 1.2 volts. It can vary by even more than that. Okay. So if VT happens to be 0.8 volts and let's say the current factor doesn't change at all, what happens? This VGS minus VT will be 3 volts minus 0.8, which is 2.2 volts. Okay. So this GM will turn out to be 220 microsiemens. So I hope it's clear what I am doing here. In our circuit, VGS is fixed and we thought that VT was 1 volt for our transistor, but who knows, when you buy many transistors, it could be 0.8 volts or even smaller. Okay. So if you do apply the same formula with Vt being 0.8 volts, you will get 220 microsiemens. And similarly, if Vt is 1.2 volts, VGS minus Vt is smaller than what is required, it's 1.8 volts, and Gm will be 180 microsiemens. Okay. So you can see that instead of 200, we are getting either 220 or 180 or some value in between. Now we have not even taken into account the variations in mu and Cox. Okay. So if mu and Cox varies by, let's say, plus 10%, if it is higher by 10%, then Gm will also be higher by 10%. And similarly, if this value is lower by 10%, the Gm will also be lower by 10% and so on. Okay. So basically, Gm is proportional to mu and Cox W by L, and any variations in mu and Cox, by the way, like I said, mu is the mobility of the semiconductor, and that varies quite a bit with temperature. Okay. So there are a couple of things here. One is that the value of Vt may not be known exactly. One possible way, though tedious, is to, when you buy a transistor, you somehow measure Vt and then you design your amplifier. Even that doesn't solve your problem, because over temperature things will vary. Okay. So let's say you measure it at room temperature. Let's take this particular case. Vt is only 0.8 volts. So to get 200 microsiemens, you calculate whatever VGS is required. Okay. And then apply that VGS. And that doesn't help, because if Vt changes with temperature, this Gm will change with temperature and so on. Okay. And similarly, as current factor changes with temperature, Gm will change with temperature. Okay. So we need to have a more robust way of setting up the operating point so that the Gm doesn't vary as much as it does now. Okay.